This is the handout for Chapter 18. I want to make a few comments on a couple of charts, but spend more time on a schematic diagram. This particular chart shows you the common electrical quantities that we're learning about in the last two chapters, this chapter and the next couple of chapters, including the symbol, the unit for that symbol, which you would use in your dimensional analysis, and the abbreviation for the unit. Some of these we have yet to get to. We haven't talked about magnetic field strength yet, or inductance, for example. We've talked about all of the others. One of the things that is sometimes a challenge for students is to differentiate between all the words that begin with the letter C. You have charge, capacitance, and current, and we let the capital letter C be the symbol for capacitance, but the unit of charge begins with a word that begins with the capital letter C, the coulomb, and the abbreviation for a coulomb is a capital letter C. That's maybe the tough one that you need to keep straight. The other thing that you ought to know is that sometimes we use a V for voltage, or the script letter E for this electromotive force over here, which isn't really a force at all. So I would never use the term electromotive force. I think it's better even just to say the word oomph as a push of the charge through the circuit. Finally, because the letter O for ohm looks like a zero, we use the Greek letter O, omega, for the abbreviation for the unit of resistance. This is an old diagram from way back where they're using W for power, which would be in watts, instead of the capital letter P for power. And they're using capital letter E for volts instead of V or the script E for the EMF. I should mention two things. If you remember that V equals IR, which could also be E equals IR, or script letter E equals IR, as well as the fact that your power equals voltage times current. And of course, they're using W instead of power. That's how they get all of these substitutions for the different terms of power, current, resistance, and volts. Now, if you remember the blue box that you used as a power supply for the lab where you charged up and discharged a capacitor, or you may be doing this lab. In any case, this blue box allows you to turn a knob clockwise or counterclockwise to select the voltage that you want. And you plug two wires into that box. Now, the reason you can select different voltages is because each voltage is made possible by different resistors. And we'll get to that in just a minute. But we begin with this device over here. This is the three-pronged outlet that you would plug into an outlet, the three-pronged cord. This symbol right there that kind of looks like a rake or something is the symbol for grounding when what you're grounding is the chassis or the blue metal box. If there was a frayed wire and some of the electricity could go through the blue metal box, it would go into the ground right here rather than through you. Because if the electricity goes through you, you hate it when that happens. Now, this is a symbol for a fuse, and this is a 2-amp fuse, which means that when the current going through this wire exceeds 2 amps, this little piece of metal right here is going to melt, and that would break the circuit, and now zero current would be going through the box. This symbol over here is your switch for turning the device on and off. This symbol right here is your transformer. Remember, we were beginning with about 115, 120 volt alternating current electricity, which is the outlet that you plug this into. This transformer, this is the symbol of a transformer. Each of these little bumps would be a coil of wire, another coil of wire. They could be adjacent to each other, or one coil might be small enough to be inserted inside the other coil. And these two parallel lines would represent an iron core, which would intensify the effect of the transformer. And this transformer will be allowing you to step from 120 volts down to 12 volts. And the way that you're able to step up or step down the voltage is by going from lots of turns of wire to a relatively few turns of wire in each of your coils. And you'll learn more about that in a later chapter. Now this section right here is the part that turns the AC current into direct current, DC current. And the way that it does that is with these little devices called a diode. A diode only allows the current to go through in one direction. So, for example, you can see that the current can't go through this way or this way, because this arrow shows the direction that the diode will only allow the current to go. So that means this current has to go this way or this way as it alternates back and forth 60 times a second. It can't go backwards because of the diodes. It can only go forward. And so now we have direct current by the time we reach the right side of this part of the circuit diagram. So now we have 12 volt direct current or 15 volt direct current. It looks as I look at the maximum voltage here, it's 15 voltage. So I'm just going to erase the 12 there and turn this into 15 volts. So now we have capacitors in several places for absorbing or releasing small amounts of charge to try to keep the current as even as possible through the circuit. And now we have another switch. We had switch number 2 over here. Let's get the right symbol. Switch number 2 there. Here's switch number 1. And depending upon whether we're going here or there or there or there, we're changing the resistance from 30 to 100 to 132 ohms of resistance. And as a result, we're able to vary the voltage on this particular device so that we can regulate how much voltage we want to be able to plug into based upon where we turn the device, the knob. And that's how we regulate how much voltage we're hooking up to the external part of our circuit. This too, of course, is grounded right over here. Now, in the next or a similar screencast, we're going to look how to solve complex circuits using Ohm's law and the principles of hooking up resistors in series and in parallel.